Okay, so here in this video, we're going to talk about the sum and difference formulas. So first we'll discuss the cosine of the difference of two angles, which is the identity that you see here that it's boxed. And so it's a non-trivial identity because it cannot be derived from the basic fundamental identities. And so here I'll try to give a quick proof of this using the unit circle. All right, so consider the unit circle on the left. So remember, the unit circle is x squared plus y squared equals 1. And so suppose we have 2 points, P and Q, which are on the unit circle. And we have the angle in standard position. That's alpha. And then we have another angle in standard position, and that's beta. Okay, so imagine angle alpha intersects the unit circle at P, and the angle B, its terminal side intersects a circle at Q. And so these points would have coordinates. Since this is a unit circle, we know x is equal to cosine of the given angle, and y is the sine of the given angle. And so this point P would have coordinates cosine of alpha and sine of alpha, P. And so Q would have coordinates cosine of beta, sine of beta. Okay, and so I want to make a comment here, is that if we see this angle alpha in center position and this angle beta in center position, if you subtract the two angles, you would get the angle alpha minus beta. Okay, and the argument here we're going to make is that the length of this triangle that we formed here between the origin P and Q here, that the length of segment PQ is going to be equal to pretty much an identical segment PQ, where we're rotating this angle so that Q here corresponds, or so imagine rotating Q so that the point will end up on the x-axis, and likewise P would rotate up on the unit circle this way. And if you do this kind of translation, you'll get a similar image that's on the right here, where we have translated Q all the way to the x-axis, and then as we rotated Q, we also rotated P, and so we ended up with this triangle here. Okay, where that angle, the angle there is going to be alpha minus beta. Now the thing about this now is this angle is in standard position, and we see that point P now would have coordinate cosine of alpha minus beta, and the y coordinates would be sine of alpha minus beta. And then Q would have coordinates 1, 0. Okay, and so the argument we're going to make here is that the line segment between P and Q here, in both pictures, these two line segments, the lengths of those line segments are going to be equal. All we did was like a rotation, but the angle and the length there are preserved. And so the idea is that the length of PQ is going to be equal to the length of PQ on both of these circles here. Okay, and so if you recall how to find the length between 2 points is using what's called the distance formula. And so that's equal to the square root of x1 minus x2 squared plus y1 minus y2 squared. And so so PQ, the length of the PQ of the circle on the left would have coordinates, right? x1 and y1 there, and then x2, y2. And so the left-hand side, we would have the square root of cosine alpha minus x2, which is cosine beta, and then you would square that there, plus sine alpha minus cosine, not cosine, but sine beta. That length would have to equal to the length of the circle on the right, but this time the coordinates are expressed as cosine alpha minus beta and sine of alpha minus beta and 1, 0. Once again, that's just the definition of on a unit circle, the x and y coordinate are just cosine and sine. And so we get the line segment here this time where we have cosine alpha minus beta minus the corresponding exponent, because that's like our x1 there and our 1 is our x1, x2 there. So subtract 1 and then you square it, plus our y1 or y2 minus y2. So then we would have sine of alpha minus beta minus 0, and that would be squared. Okay. All right, so since we have the square root equal to the square root, we could square both sides and basically get the radicand of whatever under the square root. So I'm going to not write technically that square root anymore, because we could easily just get rid of those the square root by squaring both sides. So what we're left with then is this term plus this term, and we're going to expand that term. So we would have cosine squared alpha minus 2 times cosine alpha cosine beta plus cosine squared beta. That's this term expanded out. In other words, if you wrote cosine alpha minus cosine beta times cosine alpha minus cosine beta and then do the following or multiplication there, you would end up with this. Likewise, we would do the same thing for this term here. So doing so, we would get sine squared alpha minus 2 times sine alpha sine beta plus sine squared beta. Okay, so that term would be the sine alpha minus sine beta squared. And on the right hand side, we would have, just expand that out, so we would get cosine squared of alpha minus beta, and then minus 2 cosine alpha minus beta, because you have the cosine alpha minus beta times 1, and you're getting that term twice. And then, of course, negative 1 times negative 1 gives us that plus 1. And then this term here is simply just going to be plus sine squared alpha minus beta. All right, so I'm going to collect some terms around here, because notice we have a cosine alpha and a sine squared alpha. Oops, not cosine alpha, but sine squared alpha. So that's this term and this term. And then I'm also going to collect my cosine squared beta. So that's that term, along with the sine squared beta. Okay, and then that would leave us with minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. And likewise, on the right hand side, we have the cosine squared alpha minus beta, and then combine that with the sine squared alpha minus beta. That leaves behind the minus 2 cosine alpha minus beta plus 1. The reason why I'm collecting those is because each one of these pairs here are equal to 1. Okay, And so we're left with 2 minus, and they're equal to 1 because of the Pythagorean identity. Okay, so we have 2 minus 2 cosine alpha cosine beta minus 2 sine alpha minus sine beta, excuse me. And the right hand side we have a 1 plus 1 there, so we're left with minus 2 cosine alpha minus beta, and then 1 plus 1 gives us plus 2. So there you can see the 2's on both sides would cancel if you subtract 2 on both sides. And this left hand side here, we could factor out a negative 2. And that leaves us with cosine alpha cosine beta plus sine alpha sine beta. And then, of course, the right hand side is minus 2 cosine alpha minus beta. And so if you divide both sides by negative 2, you get the identity that we want. So cosine alpha cosine beta plus sine alpha sine beta equals to cosine alpha minus beta. And that there is the difference of two-angle cosine formula, which is what we wanted to prove up here in the box here. Okay, so that's definitely it's not a trivial one that arises from the fundamental identities, but here we were able to generate it using this particular argument here. And likewise, from this we could generate some other formulas as well. Let's see how to use this formula though. We're asked to find the exact value of cosine of 15 degrees. Okay, so let's just note that 15 degrees can be written as 45 degrees minus 30 degrees. So we have cosine of 15 degrees equal to cosine of 45 degrees minus 30 degrees. And now we could apply our identity that we just derived. And so we have cosine of 45 degrees times cosine of 30 degrees plus sine of 45 degrees sine of 30 degrees. And these are nice multiple angles or special angles that we should be familiar with. Cosine of 45 degrees is root 2 over 2 times cosine of 30 degrees, which would be root 3 over 2, plus sine of 45, which is root 2 over 2. Sine of 30 degrees is 1/2. And so root 2 over 2 times root 3 over 2 is root 6 over 4, plus root 2 over 2 times 1/2, which is root 2 over 4, which we can write as root 6 plus root 2 all over 4. And so that's the exact value of cosine of 15 degrees. Okay, that's using this identity, for the difference of angle identity for cosine. Likewise, another situation we can use it is an expression like this here, where we have cosine of 80 degrees times cosine of 20 degrees plus sine of 80 degrees and sine of 20 degrees. And so we can pretty much use the fact that this here is basically the right hand side of our identity, and we can go backwards, okay, since it has that form. In other words, what I'm trying to say is that this here is the same thing as saying cosine of 80 degrees minus 20 degrees, which gives us cosine of 60 degrees, which is a nice special angle that we are all familiar with, which would give us cosine of 60, which is 1/2. Okay. All right, here in the next exercise, we're asked to verify the identity cosine of alpha minus beta over sine of alpha times cosine of beta equals cotangent of alpha plus tangent of beta. I always just choose one side and work to get to the other side. And I always like to work with the side that has more to work with. And so I'm going to choose the left-hand side to start with. So the left-hand side, we have cosine of alpha minus beta all over sine of alpha times cosine of beta. And since we have a cosine of alpha minus beta, it probably makes sense to rewrite that so that we just have trig functions of alpha and beta and not a difference of alpha minus beta. Okay, and so to do so, we would have cosine of alpha, cosine of beta, plus sine of alpha, sine of beta, all over sine of alpha, cosine of beta. All right, so then I'm going to split the fraction, meaning take the denominator both into that sum, so that the first quotient would be cosine of alpha, cosine of beta, all over sine of alpha, cosine of beta, and then plus sine of alpha, sine of beta, all over sine of alpha, cosine of beta. And then we can see that the cosine of betas for the first quotient there would cancel. In the second quotient, we would have sine of alpha canceling. And that would leave us with cosine of alpha, sine of alpha, plus sine of beta over cosine of beta. All right, well, cosine of alpha over sine of alpha is just cotangent of alpha. And then sine of beta over cosine of beta is tangent of beta, which is the right-hand side. And so we have just verified the identity. Okay, so this particular identity formula that we just derived can be used to derive, for instance, the other formulas as well, and can be used to derive, say, 2 and 3 and 4 there, just to kind of give you an idea. So once again, these are called the sum and difference formulas for cosines and sines. And so likewise, if we derived number 1, but if we wanted to derive number 2 here, basically we would use number 1, right? Because alpha plus beta is the same thing as alpha minus a negative beta. And so cosine of alpha plus beta can be thought of as cosine of alpha minus negative beta. And then you could use the fact that cosine is an even function and sine is an odd function to get this one here. And then we know sine and cosine are cofunctions identities, and so you could use the cofunction identity to help derive the sine, the 3 and 4. But I'll leave that as an exercise for you guys. Okay, so the next example here, we're asked to find the exact value of sine of 7 pi over 12 using the fact that 7 pi over 12 equals pi over 3 plus pi over 4. And so we could use the sum formula for sine. Okay, so we have sine of 7 pi over 12, which is equal to sine of the sum of pi over 3 plus pi over 4. Okay, so this tells us that using that trig identity, we have sine of the first angle times cosine of the second angle plus cosine of the first angle times sine of the second angle. And those are nice angles there, right? Pi over 3 and pi over 4 are our common angles or special angles, which if you're thinking in terms of degrees, which will correspond to 60 and 45. So sine of pi over 3 would be radical 3 over 2. And cosine of pi over 4 would be radical 2 over 2. And then cosine of pi over 3, which would be 1/2. And sine of pi over 3, which would be radical 2 over 2. All right, so we have radical 6 over 4 plus radical 2 over 4 And so we can combine that as the expression root 6 plus root 2 all over 4. All right. Okay, let's look at the next example here. Suppose that sine of alpha equals 12 over 3 for an angle alpha in quadrant 2, and sine of beta equals 3/5 for angle beta in quadrant 1. Find the exact value of each of the following. All right, so cosine of alpha, we know is an angle in quadrant 2, and so thinking in terms of a unit circle, we could think of the angle in standard position where its terminal side will intersect the unit circle at some coordinate x comma 12 over 13, and that's because once again sine is the y coordinate if we are thinking in terms of the unit circle here, where the terminal side of this angle hits the unit circle. Okay, so based on that, we know that our x squared plus y squared has to equal 1, right? Because it's the unit circle. And so we have x squared plus y squared equals 1. So x squared plus 12 over 13 squared equals 1. And so we would get x squared plus 144 over 169 equals 1. All right, subtract both sides there. Subtract 144 over 169 on both sides to get, what do we get there? 25 over 169. And then, of course, take the square root on both sides there to get plus or minus the square root of 25 over 169, which would be 5 over 13. Now, how do we decide whether it's positive or negative? Well, we know alpha lies in quadrant 2, and x has to be negative there. And so this answer is negative 5 over 13. Okay, in other words, cosine is negative 5 over 13. All right, likewise, we want to find cosine of beta. Now, cosine of beta, we know beta, if we're thinking unit circle again too, is an angle whose terminal side lies in the first quadrant. So it lies there, that's our beta. And it would intersect on, we'll have coordinates x comma 3/5. And once again, using the unit circle fact that x squared plus y squared equals 1, we have x squared plus 3/5 squared equals 1. So we get x squared equals 9. Sorry, x squared plus 9 25ths equals 1. And so we see x squared equals 1 minus 9 over 25, which would be 16 over 25. And x equals plus or minus the square root of that number, which would be 4 over 5. And so we know that x has to be the positive one since beta falls in quadrant 1. Okay, which means cosine of beta is 4 over 5. Okay, so C here, we're actually finding cosine of alpha plus beta. So we're going to use our identities. So the sum of two angle identity for cosine. So we know from the table over here that cosine of alpha plus beta is equal to cosine of alpha times cosine of beta minus sine of alpha times sine of beta. So we would get cosine of alpha times cosine of beta minus sine of alpha times sine of beta. All right, so, well, we just found that cosine of alpha was negative 5 over 13. And cosine of beta we found to be 4 over 5. And we know sine of alpha from the given information was 12 over 13. And sine of beta was 3 over 5. So we have negative 20 over 65 minus 36 over 65, which gives us a negative 56 over 65. And so cosine of alpha plus beta is a negative 56 over 65. Part D here, which I'll do over here below, so I have more space. Sine of alpha plus beta is the same thing as saying sine of the first angle alpha times cosine of the second angle beta, and then plus cosine of our alpha of the first angle times sine of the second angle beta. All right, well, sine of alpha we know is 12 over 13, and cosine of beta, which we found to be 4 over 5, and then plus cosine of alpha is negative 5 over 13 times sine of beta, which is 3 over 5. So we got positive 48 over 65 minus 15 over 65. And so we're going to get a 33 out of 65. So 33 over 65 is sine of alpha plus beta. All right, moving on to the sum and difference formulas for tangents. So tangent of alpha plus beta is equal to tangent of alpha plus tangent of beta over 1 minus tangent alpha tangent beta. Similarly, tangent of alpha minus beta is equal to tangent of alpha minus tangent of beta all over 1 plus tangent alpha tangent beta. All right, not sure if it's essential to know these formulas and memorize it, because you could, if you knew, say, the formulas of cosines and sines here, we know tangent is just sine over cosine, so you kind of have a formula already for it. But in any case, we're going to use this formulas to verify the identity here. So we're asked to verify the identity, so we'll take the left-hand side, since it looks like we have more to work with there, or maybe we don't have more to work with there, but we definitely have a difference of 2 angles there, and somehow have to get rid of the power 4 to get just tangent of x. So I'm assuming that we need to work with the left-hand side and apply the tangent, the difference of angles formula for tangent. And so we'll take tangent of x minus pi over 4. Okay, so we have alpha minus beta there, right? So then we know that we would have tangent of the first angle alpha, which is just x, minus tangent of the second alpha, or excuse me, second angle beta, which is pi over 4, all over 1 plus tangent of the first angle, which is just x, times tangent of the second angle, which is pi over 4. All right, well, tangent of x, there's nothing we could do there, but tangent of pi over 4 is a special angle. It's the angle, if you're thinking of a unit circle, it would be the angle where that hits the unit circle at root 2 over 2, root 2 over 2. So the ratio of those two coordinates would be 1. And so we're left with 1 there. And then 1 plus tangent of x times tangent of pi over 4. Once again, it would be times 1 there, because tangent of pi over 4 is 1. All right, so it looks like we have what we want already, because we have tangent of x minus 1 over 1 plus tangent of x. And see, and that's definitely the right-hand side, and we are done. Okay, that's it for this video.